Today I'm going to talk a little bit more about various methods for creating large galaxy catalogs and testing them. And then tomorrow I will primarily be focusing on using these simulations. So I'm going to cover a lot of different methods, and there's a lot of material, and some of it's technical. So feel free, please interrupt and ask questions about anything that I say. So what I want to do is just kind of give you an overview of the different kinds of approaches that we've been pursuing, and some that other people have as well. So I told you yesterday about this basic idea that if you have a high-resolution cosmological simulation and you have a volume-limited spectroscopic survey that you can test it with, we've shown that you can do this very well in a lambda CDM model with just 3 parameters. Okay, so those parameters are basically the choice of your halo property that you think is most tightly correlated with luminosity or stellar mass. Alternatively, you can think of that parameter as a difference between the stellar mass given some halo property for satellites versus centrals. The second parameter is the scatter in galaxy properties at a given halo property. And the third is a parameter which describes how much halos can be stripped before they fall below the observable mass limit of your sample. And you can test this model by looking at, for example, the galaxy-galaxy correlation function, the group luminosity function. That's what we showed in this paper, which appeared last night. People have looked at other statistics and compared them to similar models. This has never been done with all of these statistics in one unified framework, but people have also, for example, looked at galaxy-galaxy lensing. We looked at that several years ago. 3-point statistics. Joel mentioned that in the Trujillo-Gomez paper, using the same simulation, they also looked at the Tully-Fisher relation. So a lot of very, very useful cross-checks, and I think that this is telling us that we're getting very close to actually being able to do this, at least in this simple case. Okay, but remember, this is sort of the simplest case. It's where you have a high-resolution simulation where you can resolve all of the substructures. You're only focused on one galaxy parameter, and you have a volume-limited spectroscopic survey that you can test it with to put limits on those parameters. And I think in this simple case, we really sort of are now knowing how to do this right. But of course, we'd like to do it in substantially larger volumes. We'd like to understand the cosmology dependence. We'd like to know, can this be modeled without these very high resolution simulations? Think about evolution, all of these things. So first, let me just remind you of the galaxy statistics we're talking about. I think the fundamental thing is that any galaxy catalog that you create, we now have enough data from a variety of surveys to really test in detail whether these models work. Now, the most basic tests of those things are just, for example, looking at, does it have the right luminosity function? Does that luminosity function evolve in the right way? Does it have the right distribution of colors? And those really basic statistics are still extremely hard to get right in models that are sort of based on fundamental physics. In a hydrodynamical simulation, you can't yet do a cosmological volume and get all of those really basic statistics right. And that's why I personally have been driven to spend more of my effort on these more empirical models where we can test those and then use them to infer the more physical properties. Yeah, I think that's true. Yeah. Right. I don't think it's even been done for one galaxy.
Well, you come
close. Close. I agree.
But if you want us to run it down to ratio 0, that would be
Yes. Okay, but if we, for the moment, throw out the physics of star formation and feedback and all of those things, and just are interested in constraining the connection between observable properties of galaxies and the dark matter distribution, which we think we can measure, then we've got tons of ways to test this. The data is extremely rich. Okay, so beyond these basic statistics of luminosity functions and color distributions, you have the two-point correlation functions as a function of all of your galaxy properties. You, of course, have higher order statistics, endpoint statistics. I talked already about this conditional luminosity function, which you can think of more simply as just what are the properties of central galaxies in groups and clusters, and what are the properties of satellite galaxies in groups and clusters. You can look at the cross-correlation between galaxies and clusters. You can look at galaxy-galaxy lensing, which then actually provides some direct information about the mass distribution. And all of these can be used to compare observed and simulated data sets, and various people have efforts towards that. So I'll mention a few of these. This is from a study using Cosmos data led by Alexei Liatod, where we combined the stellar mass function, the galaxy clustering, and the galaxy-galaxy lensing. In this case, we just tried to constrain the underlying relationship between the typical stellar mass of a central galaxy and the halo mass of that galaxy in a fixed cosmology. Yeah, great. So the Cosmos field is a 2 square degree field, which has fairly deep HST data and also fairly deep ground-based data. Exactly. And so this is one of the few fields of the sky where you actually have deep enough optical data that you can do galaxy-galaxy lensing out to high redshift. You can do it in Sloan out to, redshift 0.2-ish. And in Cosmos, you can do it roughly out to redshift 0.9. So here you can use this combination of statistics to constrain the underlying parameters of your halo occupation distribution in the basic manner that I described yesterday. Yesterday, I just talked about essentially using the correlation function to the correlation function and the luminosity function to constrain this. Here you can add in galaxy-galaxy lensing. Now, this analysis is actually just for 2 square degrees of sky, right, as we were just discussing. And so if you imagine now doing this with 2,000 square degrees, which you'll be able to do with the next generation of surveys, you can imagine that you can get very, very tight constraints on this. And I think one of the most exciting things is that potentially you can use these kinds of approaches to actually use the small-scale information of galaxies to also give joint constraints on the galaxy halo connection and cosmology. So I just want to give a couple of examples of this. This has really only been discussed seriously in the literature in the last couple of years. For a long time, people have only talked about cosmological probes on very large scales. You just say, well, it's too complicated on small scales, so I don't want to worry about that. And it's true that it's complicated, but we know how dark matter clusters even on small scales. So I believe that one can proceed this way. So this is a specific example of how you can do this. So this is showing you that if you just look at the clustering of galaxies, okay, so the top plot is again this plot I've been showing, which is the 2-point function of galaxies. In these dotted lines, I'm showing for different values of sigma 8, what is the dark matter clustering, okay? And what you see is that you can, let's imagine that you have a measurement of the correlation function given by these red points. You can jiggle your galaxy bias in all of these cosmological models such that it matches that clustering. Okay? So the clustering alone cannot tell you anything about the value of sigma 8. Might maybe tell you something, but can't tell you very much about the value of sigma 8. But when you jiggle those, given this dark matter clustering, to get this galaxy clustering, you change the underlying HOD. Okay? You change the relationship between galaxies and halos. Okay? So then what you need is some other observable which breaks that degeneracy between galaxies and halos. And this is one example of such an observable. This is the relationship between the mass in galaxy clusters and the number of galaxies. Let's say above some luminosity limit. Let's say above the same luminosity limit with which you measured this galaxy clustering. Okay, and so the basic point is that even though these give the same observable here, they give very different measurements for the mass to number ratio. Okay, and yeah.
There are probably a few people here who aren't totally familiar with HOD. So a little description of your middle plot.
Yeah.
Mainly the one galaxy part and then the many galaxy part.
Yeah. So I
suspect you're going to come back to this.
I am, and I talked about this yesterday, but you're right that I probably should review it. So let me just explain again what this plot is. Right, what this plot is the average number of galaxies, let's say above a given luminosity threshold, as a function of halo mass. Okay? And so what you see here is it has this characteristic functional form. Yesterday I described to you that almost all galaxies have a functional form which looks like the functional form you get from how subhalos populate host halos. And always n goes as m for subhalos, and then some sort of threshold here. For where you get central galaxies. It's almost always the case that you get central galaxies, you get sort of one galaxy, roughly about a factor of 20 lower mass from where you get a factor of number of 2 galaxies. But that's a parameter in the model. Now, it's a key point that this better be, this is generally parameterized, and your parameterization of this had better be very precise if you want to use this thing. So this is one of the tricky issues in this whole game, is that you have to believe that you're doing this kind of modeling right, and so that has to be extensively tested. We've done some preliminary tests of this to just show that this can work. This is work done with Rachel Reddick and Yu Liu, who created these SAMs, and Jeremy Tinker. So this is just showing 3 random galaxy models. 3 models that may or may not look anything like our universe, but they have a luminosity function, and they have a correlation function, and they have different mass to number ratios. You can then analyze those observables and figure out whether you get the underlying cosmology in your simulation. And we show here that at least certainly within the 1 sigma error bars for these 3 very different models, you extract the same cosmology from the simulation. Okay? So this is just an example of how you can use these kinds of simulations to test this, and how this kind of extra information can provide more cosmological information. There was a very nice series of papers on the archive just in the last week or so, which I have not fully read, but I've heard them talk about it before. And this is work by Frank Vandenbosch, Ho-Jin Mo, Sirhood Moore, Marcelo Cacciato. And so they have this is a similar idea in the sense that what they're doing is they have some parameterization for how galaxies populate halos. In this case, they parameterize the conditional luminosity function. Again, just reminding you what that stands for. That's just what are the central galaxies in halos and what are the satellite galaxies in halos. And the 2 observables that they consider are the galaxy clustering and the galaxy-galaxy lensing. Very similar to what we did in Liautaud et al., but here they're marginalizing, they're essentially, instead of asking what's the galaxy halo connection, they're marginalizing over the galaxy halo connection to get cosmological constraints. I'm not showing the cosmological constraints here, but you can go look at the paper. They essentially find, using Sloan data, that they're consistent with other sort of techniques, and I think this has some interesting power. Here they have this analytic model for the conditional luminosity function, and it's interesting to note that I've only done this comparison by eye so far. I'll ask Rachel to do it in detail. But the satellite fraction that they get as a function of luminosity and the typical luminosity that they get as a function of halo mass are in pretty good agreement with what we get from using completely different assumptions, right? Using, in our case, a high-resolution simulation that's just constrained by the clustering and the measured conditional luminosity function. In this case, they're using galaxy clustering and galaxy-galaxy lensing to get this back out. So I think it's encouraging that these things seem to be pointing in the same direction. This has the unfortunate thing that there's a lot of parameters, right? So there's about 10 parameters generally to parameterize a conditional luminosity function in a given redshift bin, okay? And then you have to know how that evolves. So it's non-trivial to really be able to have your parameterization be flexible enough and also explore this. But I think this is a promising area. And the main thing that I want to convince you of is that we are at least converging on a consistent story here. And this is sort of one bottom line plot of many, many different techniques for constraining the relationship between central galaxy properties and their halos. So this plot shows on the x-axis the halo mass, and on the y-axis the ratio of stellar mass to halo mass. So it's the fraction of the total halo mass that is in stellar mass of the central galaxy as a function of halo mass. And there's lots of different techniques on here. They use different observables. The ones that I talked about yesterday, there's constraints, other independent constraints that are based on the HOD and abundance matching. And there are several other measurements. Actually, there's a few measurements that are not on this plot that are just from galaxy-galaxy lensing that get fairly consistent results. You can see there is some scatter here. And I think actually the biggest uncertainty at this point is just what is the meaning of stellar mass. So the biggest difference between the results of all of these is just in the stellar mass function that was used. If you went into every study and sort of reassigned every galaxy with the same stellar mass, I believe the points would look much, much more similar to each other. And so this is something that we need to think about. Yeah?
Again, I think something that everybody should appreciate from this is what the numbers are. And the numbers are between 2 and 4% at the peak, which is halos of about 10 to 12 solar masses. And what does 2 to 4% mean? Well, the cosmic baryon fraction is about 16%. So what this is saying is that you can hardly convert more than about 20% of the baryonic mass to stars in realistic galaxies. That's only if in the mass range, in the halo mass range, of about 10 to 12 solar masses. Above and below that, the fraction of stellar mass, the baryonic mass that goes into stars is less. And all within that spread, essentially every determination is consistent. The reason this is important is that hydrodynamic simulations tend to overproduce this by about a factor of 2 or more.
Yeah. So I think this provides an extremely useful constraint for those simulations and for semi-analytic models. Whatever physics they put in had better produce this, because this appears to be what our universe is doing. Okay, so I want to say a few words about using this kind of approach to infer the entire star formation history of galaxies, and then I'll move on to talking about modeling large volumes. So here I'm going to focus on still small volumes, where you actually, in very deep surveys, can measure stellar mass functions and star formation rates for a decent number of galaxies. And this set of plots just shows a compilation of essentially all of the data in the recent literature that speak to either stellar mass functions or star formation rates of galaxies. Okay, so these are stellar mass functions going all the way from essentially the reionization epoch to now. You can see that it's very, very tightly constrained at redshift 0, although, of course, there are still some important systematic errors. The cosmic star formation rate, this is just the number of stars formed as a function of redshift, and the specific star formation rate as a function of redshift in a couple of bins of stellar mass. Okay, so this is just a compilation of the data. And what we wanted to do here, this work I'm talking about for the next few slides is based on Peter Baruzzi's thesis. And paper will be coming out soon. And the idea is to use this in the cosmological context of what we know about halo merging, halo growth, and the number density of halos at every redshift to infer how galaxies evolve over time. Okay, so the basic idea is at every redshift you have some relationship between stellar mass and halo mass. You don't know what that relationship is. You just parameterize it, essentially with a parameterization that looks like redshift 0, and you let those parameters be free. You then know how galaxies grow over time, because if you can assign them to halos at one redshift and then assign them to halos at a later redshift, you know how those halos merge into each other. Okay, so from this assignment of stellar mass to all of these halos in a merger tree, you can derive how do galaxy stellar masses get built up over time, and how much of that is due to star formation. You have in your merger tree how much of it is due to merging. The rest of it you infer is due to star formation. And so then you can predict all of these observables. So the stellar mass function, the cosmic star formation rate, and the specific star formation rate, those observables that I just mentioned. We then worried a lot about the error bars. These are quite tricky, so we tried to be fairly conservative with the observational error bars. And then you compare the model to the data, and then you iterate. And in this case, our basic philosophy was to have as many parameters as we needed, not to overfit the data, but to be flexible enough such that our functional forms were not driving sort of our inference. But the nice thing is here, we're in still a relatively simple case. What we're really trying to do in this work is get the average star formation histories of galaxies, and we're only, in this case, really caring about two properties, the star formation rate and the stellar mass. Okay, so it's still fairly simple. We're doing this on reasonably small volumes, but because we've kept it simple, we actually can properly explore parameter space in a statistically meaningful way. And then you can go and ask, what is the posterior for lots of different parameters? And so this is the output of our model in the context of these various observables. So this is the stellar mass function. You can see that the model, the best fit model, matches that stellar mass function at all redshifts and also matches the data on star formation rates. The red band is the red line is a best fit model, and the red band is the posterior from exploring this parameter space. And so what this allows you to get at is the relationship between halo mass and stellar mass, not just at redshift 0, which we talked about already, but at all times, okay? And so this black line is that line that I showed you earlier. What is the stellar mass to halo mass relationship at redshift 0? These three plots are all almost exactly the same information, just shown in different ways. So this one shows the stellar mass to halo mass relationship. This one is just has the x-axis divided by the halo mass. And this plot is shown in a slightly more interesting way, where the x-axis here now, instead of being the halo mass at the redshift that you've observed the galaxy, is the halo mass that you think that galaxy ends up in at redshift 0. So the useful thing about looking at things this way is that then just immediately tells you, oh, okay, I've got a galaxy here, at redshift 3 that ends up in a 10 to the 13 solar mass halo today. Okay, and Joel was just emphasizing one of the major points of this plot is that, at redshift 0, you have a still very inefficient star formation. Most of the baryons in your halos are not turning into stars. Well, that appears to be true at all epochs. And the interesting fact is that it appears that galaxy formation in galaxies like the Milky Way is the most efficient that it ever was in any mass or at any redshift. Okay? I would say there's actually still some fair bit of uncertainty about what's going on beyond redshift 6, so you should take that with a bucket of salt. But our results at lower redshift are not really sensitive to what we do there. So it's actually, but this is interesting that it sort of always never has a peak more than a few percent. You can see the basic features of this plot sort of tell us these basic things about galaxy formation. We know that some feedback process has to be going on at high mass, and some feedback process probably has to be going on at low mass in order to not form stars as efficiently in all of those halos. So we get not only this connection, but we get some information about the star formation histories of galaxies. So what this plot shows, the color corresponds to the star formation rate of galaxies at a given halo mass and redshift. So the typical trajectory of a galaxy goes through these white lines. Those are the average accretion histories of dark matter halos. So a halo that ends up at 10 to the 15 today was roughly 10 to the 11 at redshift 8. That's just the average accretion history. A typical Milky Way halo was roughly 10 to the 10 at redshift 6. And so if you follow these histories, these white lines, it tells you they move through this star formation rate. So these massive galaxies had their star formation rates peaking at very early times, and the low mass galaxies kind of more piddled along. They peaked at later times. And this is, Joel touched on this in his lecture in the first day about how the difference between what happens in terms of hierarchical growth between galaxies and halos. And the basic fact is that even though high mass halos grow later than low mass halos, because the star formation rate has this basic feature, they form their stars early. Okay. No, the color is the inferred star formation rate for this stellar mass, for this halo mass and redshift that matches all of the observations that I told you. Yeah. It's inferred from observations. Exactly. Exactly. Yeah, no, exactly. It's by definition a smooth function. And you know, this is essentially the same information just plotted in a different way so that you can see the star formation histories directly. These are the star formation histories of galaxies that end up in various mass halos. So you can see the peak of star formation goes down, goes to later and later times as your halo mass goes down. And that's this downsizing, basic downsizing idea. And so there's a lot of details here, and I'm happy to talk to any of you offline, or you can ask Peter. But the basic message that I want to tell you about this is that sort of the cosmological framework of halo growth provides for a self-consistent model of the star formation histories, merging histories, and stellar mass growth. And currently, this is just constrained to sort of global statistics, and we're just talking about average properties. But in principle, you can use this approach to model individual histories and model additional observables. Here, we only constrain to these global statistics. We didn't constrain to anything having to do with clustering statistics. At low redshift, at redshift 0, where we can test that well, we've shown that this model essentially gets the same results as the model that I told you about yesterday, which is constrained by these detailed clustering statistics. But there are key things that we don't know at high redshift. So an example is the scatter between stellar mass and halo mass. That is a parameter in this model, and it's constrained, but it's degenerate with a lot of things. It's degenerate whether galaxies are falling out of your sample, what's happening. I think we've done a reasonable job of accounting for that, but in order to really test that, you're going to need to actually look at the galaxy clustering, at the lensing, at the conditional stellar mass functions at high redshift, and that will provide very detailed tests of this model. Okay, so now I want to talk to you a little bit more about modeling very large volumes. Okay, so I'm going to focus on what I've been working on for a while, which is the DES simulation pipeline, but I think this is generic to the kinds of things that need to be done for large surveys, of which DES is only one. And the basic point of this is that if you want to know how to use data to infer cosmological parameters, you better know what is the prediction for those observables given your cosmological parameters. Okay? And I just flashed this very quick because I mentioned it yesterday. I just wanted to have in my slides the basic statistics of DES. The key point here is that it's the first experiment that's sort of trying to do all-in-one galaxy lensing, so shear statistics, galaxy clustering, galaxy clusters, and supernova. I mean, that has been done to some extent in the local universe by Sloan, but this will do it out to redshift 1 and really measure dark energy independently with all of these methods. Of course, it's a galaxy survey. It will measure 300 million galaxies. I think there's actually going to be a lot more interesting science than the dark energy science, including some very interesting things in the local universe, some very interesting things with very massive galaxies at high redshift. Okay, so what are we trying to do with these simulations? So the first thing is that we want simulations that allow us to do a realistic cosmology analysis for all of these different measurements. So in the same simulation, we want to be able to measure galaxy clustering on large scales. We want to be able to detect galaxy clusters in a similar way as they will be detected in this optical data. We want to be able to do the lensing. And so we want to produce the observed properties of galaxies on large scales with a realistic impact of shear and as many relevant observational systematics as possible. And as I mentioned yesterday, as I emphasized yesterday, we want to be able to do that more than once because we don't know all of the answers. We don't know what the cosmological model is. We don't know whether we've got our galaxy model right. I mean, in fact, I would say we know we have it wrong in detail. And we don't know what the impact of lots of observational effects are. And just to remind you of this very complicated plot that I showed yesterday, you know, it would be awesome if you could do a simulation like Bolshoi and do it over this kind of volume, but then you're sort of in this regime over here to even do it once. And this is just not where we're at today with today's computers. We will be moving in this direction, down this line to larger and larger particle numbers. And it may be that, you know, in 6 years we can do a simulation that's on this line, but we still won't be able to do many of them. And there's a really, really basic point that's obvious, but it matters for this, so I just want to state it. Simulations are volume limited, and surveys are magnitude limited, right? And that means that, you know, in the universe, when you look for something, when you do a survey like Sloan or DES or LSST or any of these surveys, you have many more bright galaxies in the nearby universe, many more faint galaxies in the nearby universe here. So what that means is you either have to have methods that work over a range of resolutions, or you have to have a multi-resolution simulation. I think that the idea of multi-resolution simulations are very interesting, and we've been thinking about them specifically for this purpose. I mentioned a specific example yesterday of multi-resolution simulations just focused on galaxy clusters, and other people have done that for individual systems. But I think there's a lot more interesting things to do here. But anyways, this is part of the challenge, especially when you have a photometric survey. With a photometric survey, you don't know the true redshifts, and you can always get confused. So what you want, you know, you don't know. Let's say I only care about things at redshift 1. You don't know that you can't rule out the contaminants of high redshift galaxies, or you know, you don't know whether these small galaxies at low redshift might be measured wrong and messing things up. Lots of interesting things. So you really would like to be able to model as much as possible this full population. So the first goal is to just get, so here we're focusing on populating large volumes. So we're going to start with just, you know, global statistics, getting the luminosity functions, the color distributions right, and then starting to look at all of these details of the clustering statistics that I mentioned. So here's the basic pipeline that we have, and this is the hard work here has been done very largely by Michael Busha and Matt Becker, also Brandon Erickson at Michigan. Matt Becker is a graduate student at Chicago. The three of them have been doing the hard work. Michael's been working with me for a long time on the galaxy models. So the basic idea is to build full n-body light cones out to high redshift. We actually write the light cones directly as we run the simulations. Because we can't do the full simulation we want, we do those simulations in pieces, as I'll tell you in a moment. We then add galaxies, and I'll say a little bit more about how we do that. We then add shear at every galaxy position. Okay? So the galaxies have shear, magnification, and shifts, and occasionally, rarely even duplication that comes from the lensing. We add realistic masks. We add shape, noise, and size, and then thinking about lots of other observational effects. Okay, and so these are not really, some of these things are specific to DES, for example, the DES mask, but most of them are really generic to any such large survey. And as I mentioned, we don't just want to do this once, so we have a plan to do what we're calling the blind cosmology challenge. Okay, and so the idea is to throw several simulations at the collaboration and ask them to tell us the cosmological models of those simulations based only on the kind of information that they would have in the real universe. Okay? So the first thing will be the visible cosmology challenge, where we give them one catalog with a known cosmology. And This allows one to test your code, make sure if you get it wrong, you try to figure out why. We can continuously update the model for the galaxies as our knowledge of the actual galaxy population in the universe evolves. And then we will do a handful of simulations where we don't tell anyone anything about the cosmological model except for just what they can infer from the galaxy population. So again, the idea is you've got a set of galaxies, you've got G, R, I, Z, Y colors, and that's it. So then the idea is to do coordinated analysis with the various working groups to see if, for example, they get the same answer, to see whether that answer is the correct one. I'm guessing that this is going to be a long process. We're going to start it this fall. We've released a preliminary version of the first simulation to the collaboration already, but I think this is going to be something where really nobody knows how to do things at this level of accuracy with this many galaxies, and so I'm sure there will be issues. One of the issues is trying to put in the observational systematics that you think exist. So that's something that we've done some of and we'll be thinking about more. I'll say a few more words about that. So I just want to give you a sense of all of the steps that go in here. So one decides on a cosmological model, runs the initial conditions, runs the simulations. We output the light cones directly. We run a halo finder on those light cones, make sure everything looks sensible. We add galaxies. We run some validation tests, make sure those galaxies look sensible, calculate the shear at all of the galaxy positions, add shapes, and then lens and magnify those galaxies. We add stars. The things done in red are things that we've discussed and in some cases have plans for, but have not actually done. We add a mask. Right now, we're just using a very, very simple mask, but the plans are to add a mask which actually varies the photometric depth and the seeing and things like that. You'd like to put in other various observational effects, like the fact that you don't always know that a star is a star and a galaxy is a galaxy. We're thinking about ways to do that. Determine photometric information, run a few different photometric redshift codes, and then we provide in some database these various properties that are supposed to be just the observed properties. And then people do analysis on that. So I'll say a few more words about each of these steps just to give you a sense of what's involved. So here we decided that we wanted to do simulations that were fairly tractable so that we could do them multiple times. So we have 4 simulations of varying resolution that go out to redshift 6. We're not really trying to do any dark energy science beyond redshift 2. So the high redshift simulation is fairly low resolution. It's really just to make sure that you have those background galaxies in there. And we do one simulation that's fairly high resolution to tune the model, which essentially is done by determining what is the galaxy halo connection in this high resolution simulation where we think we know how to do this. So these have actually been mostly run on Exceed resources. And then all of the post-processing has been done on computers at SLAC. In the last year or so, because we had this Exceed allocation, people, primarily Brandon Erickson and Gus Everard, have been working with the people at Exceed to get a workflow to go, so far, just the first part of this, which is just from initial conditions to light cones, so that you do it all automatically and it's less chance for human error. It changes the overall time that the simulations take to run. And I think sort of designing these kind of things that minimize the opportunity for human error is important in these kinds of things. So then the basic idea of the galaxy population, as I told you, we can't in this kind of volume currently run these many simulations that resolve all of the halos and subhalos.
And so it's a very empirical method based on the dark matter density. So the first idea is you've got your dark matter particles, and you've got a luminosity function that you put in by hand. You assume something about its evolution, and you just stick those galaxies into your dark matter light cone somewhere. Okay, so the question is where? We do use the halo positions to put in brightest cluster galaxies. And then we have a relationship between, what we do is in a high resolution simulation, we measure the relationship between given a galaxy of a given luminosity or ranked number density, what is the dark matter density that it lives in. Okay? And this allows you to just really push your resolution to the limit. And so then all you need to do is make sure that you can properly trace that dark matter density with the number of particles that you have. This is just a quick example. So this is what the dark matter density, so this is the dark matter density. This is the scale enclosing a given density as a function of galaxy luminosity that's tuned from a high resolution simulation. You can then take this recipe and put it back into your simulation, and we show that if you do that, you're able to still reproduce the clustering properties, at least on large scales. On small scales, there's still some tricky issues that we're, but I think there we actually should be able to use the halo information. Okay, so that's just adding the galaxy luminosities. Then you need an algorithm for adding galaxy colors, and the idea here is also empirical. So once you have a catalog with R-band luminosities, you map the colors from real data onto mock galaxies using some training set which comes from that real data. So at present, we're just using the Sloan spectroscopic sample as essentially our training set. So what we do is in that data, we measure, given a luminosity and a local galaxy density, we essentially measure what is the SED of those galaxies. Currently, we're doing this using this code called KCorrect, which just takes galaxy luminosities and derives SED templates. So there's about 4 or 5 numbers that describe that SED. And so you have this probability, and then you use that to populate your colors onto your mock galaxies. And there's actually a paper on the archive today that did this for deep using abundance matching for the first step and this same color method for the second step. So those things actually are totally modular if you have a higher resolution simulation or if you have a semi-analytic model and you don't like the colors but you like the luminosities. You could imagine using this kind of technique. I don't think this is the be-all, end-all way to do this, but it works reasonably well. It's something that we definitely will be thinking about actively developing. Okay, so the nice thing is that doing this allows us then to get all the way out to these high redshifts. I want to just say a few words about the lensing that's in these simulations, and these are slides from Matt Becker, and so I'll go through them relatively quickly, but feel free to email Matt or ask me if you have questions. But the basic idea is that you want to be able to do this lensing on large areas, okay? And the problem is that actually the sky is curved on large areas, and that complicates things. So you really want to get the real redshift dependence of the shear and lensing bias correct all the way down to small angular scales. And so the basic idea is this multiple ray tracing with galaxies. Similar things have been done for small areas, and the key thing that Matt has done is extend this, made it very accurate for large areas. Okay? And so the idea is that at every source galaxy, you trace the lens plane. You have these nested shells which form your lens plane, and you trace the rays from the observer to the source. And so you compute the mass density in these things. You solve this 2D Poisson equation, and then you use that to propagate the light sources. Absolutely, yeah. Potentially. It's a little tricky to do. We've been talking about doing what we've done with Bolshoi. It's a little bit tricky because you'd have to actually, you have to create the full dark matter light cone. So you can do that with interpolation. I think it's viable to do that with interpolation. Here, we've only done it on simulations where we've actually written the light cone out. But I don't, probably that's not a dominant source of error. Yeah, so that's an interesting question. We've been doing fairly, so there's two key points. One is the resolution of the lensing, and the other is the resolution of the simulation. So you don't want the lensing to be higher resolution than your simulation, because then you're just wasting computation. Here, we've been doing this with fairly low resolution. So these are, most of what we've done so far is on the Kármán simulations, which are a gigaparsec and a few times 10 to the 10 solar masses. For most purposes, outside about 100 kiloparsecs in the interiors of clusters, that appears to be accurate enough. If you want to get the shear inside of clusters, you need higher resolution. And so you obviously can't do strong lensing with that. I mean, with high resolution simulations like Bolshoi or like Rhapsody, you might be able to do strong lensing. It's something we're thinking about. I don't think we at present want to go to higher resolution for these very large areas, but just quickly, what Matt's done, and this is essentially the results of his PhD thesis at Chicago, is figure out how to do this ray tracing for a curved sky, and it's harder than it sounds. Matt's been working on this very seriously for about 2 years, and he's extremely good. But what one has then is a full sky convergence and shear map from these simulations. And actually, I had a plot that I didn't include that actually shows someone measuring the shear correlation function coming out of these simulations, and it looks quite good. Okay, so just summarizing what we have right now. The first version of this is the beta version is done, and we plan to update it over the rest of the summer and make it publicly available sometime this fall. So this will be a simulation using 10,000 square degrees, going out with galaxies, I would say, that we trust to redshift 2. We have galaxies with multiband photometry to the full DES depth, but it's not DES specific. So we will be providing magnitudes for Sloan, Sloan Stripe 82. I list those separately because they have different photometric errors. And other surveys, if your favorite survey is not here, then let me know and we will try to add it. And what's exciting about these is it allows one to do science analysis really from clusters, lensing, and large-scale structure on the same simulation. And this is the first time we've done it. I'm sure there are 500 things that are wrong with it, but it has been, aspects of it have been very extensively tested. So there's a small version, again, based on this gigaparsec simulation that gets you about 220 square degrees out to redshift 1.3. I'm going to put that here and let you guys play with it if you're interested. And just to give you a sense of, in detail, what's in these catalogs, so there's the things you can observe, which are just magnitudes and positions on the sky, right? That's what you actually will get out of your survey. And then there's a lot of other information that you have. For example, the real shear at the galaxy positions, the halo information, the actual redshift, all of these things. And so when you combine all of these things and the multiple wave bands, the full catalogs are about 2 terabytes for about 500 million galaxies. And as I said, we'll have some, you guys can play around with this thing if you're interested. So our goal was to design these so that we could actually turn them around relatively quickly. So the idea is that we would be able to generate roughly one of these a month, Probably some of those would be done on repeats of different galaxy models on the same simulation, and some of them will be new simulations. So we plan to do at least 10 cosmological models, probably many more with different galaxy prescriptions. We're planning on sort of over the next 5 years or so to make about 100 of these. Right now we have a simple model for SE information, which has been added by the SPT folks, and thinking about developing all of these things. So I'm going to skip, let's see. What time should I finish, Joel? Okay. 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 That's fine. So I'm going to skip this part and discuss it next time. But I was going to go through a specific case of use of these catalogs, but I'll talk about it next time. So I really liked what Matt said about designing your questions in advance. And that's really essential when you're doing a simulation that you're only going to do once. In this case, we're trying to design something that's really general purpose, and I have no idea what a lot of the questions people are going to want to ask are. So I think the idea here is we've tried to think of as many questions as we can ahead of time, but what we're going to have to do is just iterate the simulation approach as those questions evolve. And I think one of the things is that those questions are very clearly going to be evolving rapidly as the data and the quality of the data and the volume of the data evolve. And so hopefully, you know, what I've sort of summarized for you is a number of different approaches for how you might populate a simulation with galaxies. And none of them are really the right answer, right? Because it really depends on which question you want to solve. So I think the goal is to be able to do this in a flexible way so that you can update this as your questions evolve. I'll just end with a few comments here. I mean, I think one thing I want to emphasize is that the data is really rich enough that we have to improve our statistical methods in the simulation regime as well as in the data analysis regime. And that's part of why you guys are here. You know, ideally, you know, you don't want to do these simulations once. You won't be able to get out the science that you want. You should be constraining all of the underlying parameters that go into the catalog production with data. And this is happening in places, but it's in its infancy still, sometimes because it's a real computational problem, and sometimes it's just because we're not there yet. You can do it for limited cases. So this is the one case that I explained to you where we actually are fully exploring parameter space, but our observables are very simple here in some sense. And we're not trying to do these large volumes. That kind of approach of exploration of parameter space is starting to happen on the galaxy formation side in semi-analytic models. So this is an example produced by Yu Liu, who's a postdoc at Stanford, who has been a pioneer in sort of the application of these Bayesian methods to semi-analytic models. And there are several groups now doing this. But it is definitely still in its infancy. You know, so the basic idea is that these semi-analytic models have maybe 15 parameters in them that specify the physics, right? So those specify things like, you know, what happens when stars form, what kind of feedback do they produce, how does the cooling work. So all of the models have, I would say, probably at least 10 parameters, sometimes 30, or sometimes just a lot of them that are chosen and fixed, and then you pretend it's just a few. But really, doing this properly needs to be where we're moving. It's not easy. Because, you know, when people do this in cosmological parameter space, typically their calculations take 1 second. If you want to run a full galaxy population to the resolution that you'd like on, for example, a simulation like Bolshoi, it takes, you know, maybe an hour. So you have to pick pieces of this problem where you actually can explore parameter space. I know the various people working on this are coming up with creative solutions, but there's still a lot of room for improvement here. And I think, you know, especially in this case when you're not really exploring parameter space, you have to be very careful about what questions are you asking and what questions are you really answering. I think that's been especially difficult in galaxy formation because for a long time we have not been in this regime where we have been exploring parameter space. And so the inference when you're not exploring parameter space is significantly harder. So I will hope that many of you in this room will be people who will think about these questions and provide solutions to them. Just along the lines of what Matt said, I mean, I think that it's exciting to me that not only are we moving towards more public codes, more community codes, also we're moving to sort of more modularity. Many of these things, you know, I think we need a lot of validation. One approach is not the right way to do it. It's great if we've got 3 different models that do the same thing and that you can actually plug and play, you know, take one out, put another one in. And, you know, in this case of the kinds of things I've been talking about, we've got simulations, galaxies, lensing, and then some way to go to what's in the truth, to what you actually observe. And all of these, you might have different choices. So it would be really great if we can design sort of methods and algorithms to work together as a community such that those things can be more modular and that we can actually test them against each other. And then this line is just expanding the galaxies piece of it, right? We know, we've discussed, we have halo finders, merger trees, ways to put in luminosities, ways to put in star formation histories, ways to put in galaxy shapes and morphologies. And again, all of these, there are different approaches. I don't think, you know, some may be better than others, but we've certainly not converged on the right answer in most of these cases. And so actually exploring multiple options and being able to interchange them is great. YT in some cases provides a really nice framework for that. I think all of these are, the codes I've listed here are just the ones that I thought of this morning that are publicly available codes that many people use. And so I think the evolution towards this is great news for the field, and I hope all of you will be involved in that enterprise. So, thanks. Joel.
Yesterday, Gerard Munson described an amazing project where they're actually creating images of galaxies of all sizes in back of lifetime. Can you compare and contrast what you're doing with that galaxy to what they're doing, and also do you see opportunities for collaboration?
Yeah, sure. So I didn't tell you anything about the image part of it. We have done some of that, but it's been a little bit different than what Gerard explained to you. What we have done is taken our simulation outputs, and we've created images that have actually been run through the entire DES data management system. And that's been done now 6 times. The data management system is still immature, I would say. But that produces images that then go to catalogs, and that really is what the system would be producing now.
So are you creating images of actual galaxies? Or how are you creating them?
Yeah, the images are essentially based on Cosmos galaxies. I think that is a very useful thing to do for specific projects. LSST, for example, has a very sophisticated image simulation program that actually takes individual photons from galaxies and evolves them through the atmosphere and through the telescope. It's an amazing piece of software. It's been years of work and is continuing. But I think that is necessary to understand LSST in detail. However, there's a very clear need for something that's much more lightweight. I mean, to run through the DES data management system, we give them these 200 square degree catalogs. It takes them 3 months to give us a catalog back. And so that's obviously not something you can do many times. So we've been thinking about lightweight approaches, but I think what these guys have done is totally awesome and certainly could be applied to the catalogs that we're producing.